Hydrogen is often called the fuel of the future, but producing it cleanly is a challenge today. Most hydrogen comes from fossil fuels. In fact, 6% of the world's natural gas and 2% of its coal are used to make hydrogen, releasing over 800 million tons of CO2 per year. That's where electrolyzers come in. They are the technology used to split water into clean hydrogen and oxygen powered by electricity, ideally from renewables. However, not all electrolyzers are the same. So today we are going deep into the electrochemical heart of green hydrogen, E for electrolyzers. At its core, electrolysis is a simple reaction. You take two molecules of water and they are split into two molecules of hydrogen and one molecule of oxygen. Using electricity, we split water into oxygen and hydrogen. But to make this happen practically, we need three key parts: an electrolyte, a cathode for the hydrogen evolution reaction, and an anode for the oxygen evolution reaction. The standard equilibrium voltage is about 1.23 volts, but due to losses, real-world systems operate closer to 1.8 to 2 volts. The efficiency, cost, durability, and flexibility all depend on the electrolyzer technology. So let's break them down. There are 5 main types of electrolyzers: alkaline water electrolyzers, also known as AEMWE. These are the most mature and historically dominant, and they use potassium hydroxide or sodium hydroxide as electrolyte. They operate at about 70 to 90 degrees centigrade and use non-precious metals like nickel and cobalt. They are low cost and durable, but they have slow startup and potential safety concerns due to gas bubble mixing. They are not well suited for fluctuating renewable power. Next, we look at proton exchange membrane electrolyzers. These are also called PEM electrolyzers. These use solid polymer membranes like naphthalene, and they require pure water and precious metal catalysts like iridium and platinum. They have a fast response and they can handle high pressures and dynamics and produce high purity hydrogen up to 99.999% and are excellent for coupling with renewable sources like solar and wind. However, they have a high capex due to scarce materials. Fun fact, to meet EU's 2030 goals of 40 gigawatts, we'll need about 20 tons of iridium, and that's over 2 years worth of global supply. Next, we look at anion exchange membrane electrolyzers, also known as AEM. These are a hybrid technology, and they use alkaline conditions in a solid membrane. They can use non-platinum group metal catalysts and use cheaper materials. However, this technology is still at an early stage, facing durability and membrane stability issues. The high pressure operation brings the risk of membrane cross permeation. It's promising for cost reduction, but needs breakthroughs in R&D. Next, we look at solid oxide electrolysis cells. These are also known as SOEC, and they operate at high temperatures between 700 and 1000 degrees Celsius. They use ceramic membranes, which are ultra-stabilized zirconia. They are high efficiency and reversible. However, the challenge is with material degradation, sealing issues, and thermal stress, and they can be used in only less than 1 megawatt projects. The materials are sourced mainly from China, which poses supply risks. And finally, we look at proton conducting ceramic electrolyzers, PCC. These operate at between 300 to 600 degrees Celsius and use perovskite electrolytes. They combine high efficiency with lower temperatures than solid oxide electrolyzers. They are limited in manufacturing scale and have poor thermomechanical properties. They're still experimental, but they are promising for future hybrid applications. Next, let's look at the market. Electrolysis currently supplies just between 1 to 2% of global hydrogen, but the market is booming. Global electrolyzer capacity is growing at 32% per year since 2010, and PEM electrolyzer capacity alone has grown at about 80% annually. Over 200 gigawatts of new projects are planned by 2040, mostly in Europe. EU alone expects 10 million tons of green hydrogen by 2030, reducing CO2 emissions by 100 million tons. Electrolyzer manufacturing could create over 170,000 jobs in Europe. What about the costs? The electrolyzer system prices are dropping fast. Currently, we have alkaline electrolyzers at between 170 to 1,000 euros per kilowatt, PEM electrolyzers between 700 to 2,000 euros per kilowatt, and solid oxide electrolyzers are the most expensive at greater than 2,000 euros per kilowatt. That costs make up to 64% of total system cost. but the balance of plants, which is the power conditioning, water treatment, hydrogen pressurization, becomes increasingly significant at scale. Research and development is focusing on different things such as thinner and cheaper membranes, low platinum group metal or platinum group metal free catalysts, which are environmentally friendly, better manufacturing and design, increased efficiency, especially under variable renewable electricity input. Here are some key players in each category of electrolyzer manufacture. For alkaline electrolyzers, we have ThyssenKrupp, Nel, and Asahi Kasei. For PEM electrolyzers, we have ITM Power, Cummins, and Siemens. And for solid oxide electrolyzers, we have Sunfire and Ceres Power. And for anion exchange membrane electrolyzers, we have Enapta. As manufacturing scales, we may see costs fall, similar to what we have seen for solar and wind. Electrolyzers are a key part of the green hydrogen economy. The challenge is clear: make them cheaper, more durable, and more efficient, especially when powered by renewables. As we push towards net zero, we need more than just electrolysis. We need smarter materials, circular supply chains for critical metals, and bold policy supports to bridge the capex gap. If you found this helpful, give this a like and please subscribe to the channel. I'm breaking down hydrogen from A to Z for energy professionals and enthusiasts just like you. Up next is F for fuel cells, how hydrogen powers your car, your grid, and maybe even your next flight. I'll see you in that video.